So the other advantage of passive house is you're always going to be above code until it becomes code. So you don't have to be concerned about being in compliance with code, a new code, say in 10 years. Like if you bought an old house that only has a 60 amp electrical panel, if you don't touch anything, you're okay. But as soon as you do any renovation, they're going to make you come up to new code, which is about a 100 amp panel. So by the same extension, if you are building a house now to code minimum, we're already at, there's now a 20, we are under the 2017 energy code for buildings. There's already a 2019 energy code for buildings that's written that we haven't adopted. But the 2030 energy code for buildings is essentially net zero ready. So by building the passive house or net zero standards now, you're protecting yourself from possible future costs when you sell the house to bring it up to the new codes. Now we don't know exactly how that would be enforced and what they will make you come up to, but it is kind of insurance to be building above code now. So a little bit here about greenhouse gases, because that is another benefit of passive house. If you build a passive house, you will reduce the greenhouse gases emitted from your house. So the greenhouse gas emissions, this is for the city of Calgary. So you can see that buildings in the city of Calgary take up 62% of all the greenhouse gas emissions. And that's really because the city of Calgary and same thing with Edmonton, they only own buildings and cars. So that's going to be the biggest part. But depending on how much of a building you account for, buildings can take up between 12 to 40% of the world's greenhouse gas emissions. And that difference is just whether or not it's just like the operational cost of the building, or if you include the embodied carbon to build it and the cars to build it and move it. But basically buildings have a large impact on the amount of greenhouse gases we are releasing into the atmosphere. And so this is the advantage. Just from the energy reduction, that 90% energy reduction, you'll save about 6 tons of greenhouse gas emissions in your house per year compared to a code minimum. So it is a non-insignificant amount, and that's just operational from the energy. There will probably be more. And all my assumptions are down there. That's an average house, natural gas heating. So here's some kind of worldwide examples of passive house. This is from the passive house database. So it's a database that you can get access to, and it kind of lists all of the certified passive houses around the world. It only has 5,000 buildings, it's a few years old. So a single family in Lithuania, single family in Estonia, there's a factory in China. Like again, it's not just houses, it's all types of buildings and all types of climates can be built to the passive house standard. Here are a kindergarten class in Sweden. So it's nice to get in kindergarten, your kids having high quality environments. A single family in Latvia, another single family in Finland. So here's some, I guess, more cold climate examples. We've shown that it does work in our climate. So it's a sports complex in Sweden, a school in Sweden, and a seniors complex in Sweden. So those are some bigger complexes, multifamily, but they're all built in a cold climate to the passive house standard. Here's some more kind of closer to home. These are Alberta examples. We'll look in more detail of them later, but again, it can be done in Alberta. Now we're going to go over the 5 principles of passive house. So it's 5 principles. It's not pick 3 or pick 4. You need all of them. They need to all be applied correctly to get all the benefits out of the system. First principle is insulation. So this one should make pretty good sense. When it's cold out, we put on a big giant jacket. We put on our toque. We put on probably snow pants. We put on big winter boots. We put insulation everywhere on our body. If we happen to be in Vancouver, we would probably wear a less insulated jacket because it's warmer there. But our houses, we can't put jackets on and off our houses, so we kind of have to dress our houses for the worst case, which means lots of insulation in this climate everywhere. And what we're trying to do is, right now we're all in code minimum houses, we're all kind of living in those glass coffee pots. So they stay warm as long as there's kind of a continuous source of heat to the bottom. So the second photo is always a thermal imaging camera. So again, that coffee pot is very hot. There's like lots of heat from the bottom, keeping your coffee warm. So that's our big furnaces, keeping our coffee warm because the heat's all escaping from the glass. What we want to move towards is the passive insulation that just sits there. That's kind of your thermos or your insulated sealed cup. So you put in cold water, you put in hot water, the insulation sits there and keeps that water at that temperature for a long amount of time. You don't need energy, it just sits there and does its job forever. So that's kind of what passive house does, is you want more passive insulation. So there's obviously a large number of insulations. We won't go through all of them today. Here's kind of 3 ones that we'll talk about. They all have a similar R value. So this is one of the 2 terms I will use today. So R value. So that is the resistance of heat flow through a material. So all materials, or all insulating materials, have an associated R value to them. But when you then take all those materials, combine them with steel, with studs, drywall, OSB, tapes, membranes, when you combine all those things into an assembly, now what is called an effective R value of that assembly. And it takes into account all of the kind of R values of the different materials in it, in the areas, and it comes up with an effective R value. So when we talk about walls, you need to talk about effective R value. And the interesting thing is, before the NECB 2011 code came in, which actually Alberta only adopted in 2016, the code talked about R value. It didn't talk about effective R values. So now we are at least required by code to worry about effective R values. But that's definitely what we want to be doing. So here's 3 types of insulation. The top one is dense packed cellulose. So dense packed cellulose is recycled newspaper. It's a good product because it's recycled. But of course, since it's newspaper, you're like, oh, well, that can burn and all a bunch of other things and rot and mold. So what they do is they add borate to it, which is a kind of naturally occurring chemical, and additive. And that additive is a flame retardant. It's also mold resistant. And it also resists, or bugs and animals no longer want to eat it because it's kind of toxic to them. But it's not airborne, it stays in the product, it's not toxic to us. It doesn't off-gas. Next we have mineral wool. 2 main manufacturers is rock wool, or old Roxol. They've renamed to rock wool. And there's also Owens Corning, also has their thermal fiber material. And what mineral wool is it's basically rock slag, so a waste product from blast furnaces. And what they do is they heat that up, spin it around into basically long strings of rock, molten rock, and then they put it together in mats that becomes fluffy. So it does have insulation value because it's fluffy, because it's rock, it will never mold, it will never rot, it's very hard to chew through. And it is actually a little bit hydrophilic. It repels water because it's a rock. The 3rd one down is type 2 EPS foam. So EPS foam is kind of the white styrofoam that you're used to seeing in your styrofoam cups. Its blowing agent, or how it's made, is they just basically make bubbles with air. So it is a very low cost option as well. So with blown cellulose, mineral fiber is a little bit more. But there are other types of foam that have different blowing agents that are more chemicals inside of them, and those have slightly higher R values, but they have some other concerns with them. When you're talking about insulation, obviously R value is kind of the most important consideration, but there are other considerations you want to think about. So fire resistance, does it burn, does it not burn? How long does it take to burn? Water resistance, what happens when it gets wet? Does it mold, does it rot, does it do nothing, does it just sit there? Does the R value change if it gets wet? Does the R value come back if it dries out? So those are all things you need to worry about, or the builder that you hire needs to worry about. Does the R value change over time? So remember those the non-EPS foams. The main one is XPS and some spray foams. XPS is kind of the blue and the pink foam that you see by Dow and Owens Corning. They are slightly higher R value because they have a blowing agent or a chemical inside the air bubbles. Or it's not an air bubble, it's a chemical blowing agent bubble. The problem is with XPS, you lose about 15% of that, or uses 15% of the R value over 10 years, 5 to 10 years, by the blowing agent coming out and being replaced with air. So that blowing agent is coming out, so depending where it is in assembly, it's coming out into your building, and also you'll lose the R value. So you're paying for like an R5 per inch, and kind of 10 to 15 years later, you only got an R4.5 per inch. Spray foam does that to a lesser extent because the structure is a little more dense, so it does still lose, but not as fast. Does the mold and fungus, or is it mold and fungus and animal resistant? So you do want it kind of to be all of those things most of the time. There's very few installations that aren't these days. And the animal resistant one, there's kind of two different ways. Like the rock sole, it's hard to eat, but they can kind of pull it apart. Foam, there is no nutritional value in the foam, but if the animals can get access to it, they would love to build a house in your foam. They'll go get food somewhere else, but they want to come back to a nice warm house. So you want to make sure that if you are using foams below grade or near the grade, that you are covering them with some type of membrane or somehow stopping mice from getting in there, birds from getting in there. We don't have a lot of carpenter ants in here, but who knows, we might in a few more years. But you want to keep those animals out of your foam. Once you're more above grade, you don't really have to worry about it, but it's kind of the 1 or 2 feet right at grade that you really have to be worried about your foams becoming tunnels for homes for other things. And does allow moisture to pass through it. So this is kind of another term. It's called vapor open or vapor closed. You might have also heard the term breathable. Houses don't really breathe. It's just a more common term because of Gore-Tex. Gore-Tex is a breathable fabric. It's actually not a breathable fabric, it's a vapor open fabric. So what vapor open means, it allows water vapor to move through it. A vapor closed fabric, the best example is poly, or some other types of foam, are vapor closed, so no moisture can go through it. So that's a good thing below grade. If no moisture can get through it, then if it's below grade, you're going to be wet, but it's not a concern. Above grade, most people, for kind of safety and resilience, prefer a more vapor open wall. Vapor open wall means that the moisture can get out. The reason you might want that above grade is that no one's perfect. They're built by humans. Humans make mistakes. A blower door test will check most things, but moisture still might get into your wall. So if it's a vapor open wall, you now allow it to get out. You always make sure it's vapor open to the outside, but if you have a poly or a vapor closed vapor barrier, it means you can't dry to the inside. If you have a vapor open vapor barrier, which is on the inside, then it can dry both ways. So again, it's different considerations, different applications, but you need to think about all these things, or pay someone to. The other thing you need to worry about with insulation is embodied carbon. So right now, Passive House, again, it's only an energy efficiency standard. It does not officially care about this. When version 10 of Passive House comes out, it will have this in it. Again, we've only been worrying about this for kind of 2 or 3 years, so all the standards are kind of catching up. What embodied carbon is, it is the amount of CO2 equivalent that is released into the atmosphere in the extraction, fabrication, manufacturing, and then transportation of that material to the site. So it's basically, it's called embodied carbon. Some people are calling it upfront carbon or pre-occupancy carbon. It's basically the amount of carbon that you've released before you moved into your house. So before you've started to turn on the furnace, turn on the heater, turn on the anything, it's the carbon that you've already emitted. And the reason we need to worry about this is different insulations and different materials have different embodied carbons. So blown cellulose is carbon negative, mineral wool is a low carbon, and the type 2 EPS is kind of more of a medium carbon. So this slide, kind of gives you a more graphical representation of what that means. And yeah, kind of the big one to remember, because there were and still are some net zero builders that use a significant amount of spray foam in their building. Spray foam has a high embodied carbon. The people that make spray foam know this, and what it is, it's the blowing agent that makes spray foam come out as a liquid, basically, and expand and then solidify. So that's obviously a large chemical reaction. The chemicals in there have a very high embodied carbon. They know this, so the spray foam industry is improving or trying to improve, so they have a new blowing agent, chemical, in it that reduces their embodied carbon by 50%. All the other ones, like XPS, is used pretty minimally in passive houses and high performance buildings, basically because of the cost. Like it's R5 instead of R4, and remember it loses 15% of that, and it costs a lot more per square inch per R than EPS. EPS is the white foam, and it's got a relatively low embodied carbon for foams, and it's also very cost effective. Going further down the list, mineral wool is a little bit less, fiberglass is a little bit less, and then next we go into carbon negative materials. You're like, well, how does that work? So basically it works by being plant-based. So plants are the first and the best carbon sequestering machine. They pull CO2 out of the atmosphere, and through photosynthesis, they turn that carbon dioxide, or CO2, into cellulose in their plant structures, in their body. And then if we harvest that cellular structure from the trees or plants or straw or whatever, and put it into a building, like a passive house that's going to sit there for 50 to 100 years without rotting, without molding, without re-releasing that carbon back to the atmosphere, you have sequestered carbon. So that is how you are carbon negative. You are taking atmosphere CO2 out of the atmosphere from a plant, taking that plant, putting that plant in a building that doesn't burn down, hopefully, or doesn't go anywhere. So wool, well, wool is from a sheep. It's pretty sustainable. You just shear the wool off a sheep, and the sheep grows more. So that's why that's carbon negative, because there's not much besides a shearer to harvest it. Dense packed cellulose is getting pretty good on the negative side because it's all recycled newspaper. Cork is a little bit more because, again, you just peel it off of a tree. It's a little bit more expensive, but it has some other really neat properties because you just shave the bark, which is the cork, off of the tree. And you can keep doing that year after year after year. Hempcrete. So hempcrete is made out of hemp, which is kind of a straw from the hemp plant, or the stalk from the hemp plant. And then it's mixed with a lime plaster to turn into hempcrete. So it's similar to concrete, but actually the cement in concrete also has a very high embodied carbon. The cement from concrete is responsible for 6% of all the greenhouse gas emissions in the world, making cement. So again, the cement companies are trying to improve that. They're trying to basically kind of move off of, because you have to heat up lime to make cement. So they're trying to use more renewable energy instead of gas to heat up the furnace, and they're trying to change their chemistry to get off of it. The other way to do it is it's the cement. So if you find a alternate cementitious materials like fly ash, slag, more lime, or just basically concretes that reduce the amount of cement in them, then that's how you reduce the embodied carbon of concrete. But again, by using hempcrete, it uses a lime plaster, which isn't cement. And then the best one is straw bale. The reason it is the best, we create a lot of it, it is the stalk below the wheat. We want the wheat at the top. The straw has no nutritional value. So some animal or some people that have animals might use it as bedding for their horses, but there's generally a large surplus of straw that is already packed into a nice bale. So if you just use that bale directly as insulation in your house, that's great. There are also some people out east that are taking that straw and either dense pack blowing it in or chopping it up and making straw panels of it. But yeah, straw is one of the best ones. It's not really commercially available right now in Alberta, but hopefully it will. So that's insulation. There's one. Number 2, airtightness. Back to the analogy of putting on your warm winter jacket. What airtightness is you want to zip that jacket up. If you don't zip up your jacket, what happens is the wind comes in and all that nice warm air that you warmed up, or the warm air that you paid to heat up in your house, just gets blown out through the cracks. So that's why you want airtightness. And the way you test airtightness is through a blower door test. That's what that picture is, where basically they stick a fan in your door and then pressurize and depressurize the house, and then through some calculations come up with kind of the size of hole, that equivalent hole, or the measure is air changes per hour. So it's basically how long would it take all of the air in the house to seep out through the cracks. So passive house requires 0.6 air changes per hour or under. Code before 2011, or NECB 2011, there was no air change requirement. Now we have 3.2 air changes at 50 pascals as a code requirement. However, there seems to be so many wiggle rooms and subclauses in the code that a lot of people are still building a house without doing a blower door test. So you really don't know. And probably a few years ago, we were doing 5 air changes per hour. I've heard of a test of a recent building that was 14 air changes per hour. So that means like every 5 minutes, all of the air in your house is out of your house. Like, just leave the door open. Like, you are leaving the door open. And the 0.6 sounds scary. Once you start using the right materials and simplified details, it actually isn't. When we see the examples from Alberta, pretty much everyone's blowing kind of 0.3, 0.4. So once you start to think about it, it isn't that difficult. So how do you do that? So there's lots of different materials. So this is Rotoblast's frost tape, because we never build in the winter in Calgary or Edmonton, but this tape works to -20. So if you by chance happen to, then that's a really good option. This is a Siga tape. This is one of our other sponsors. This is their interior tape. It's called Rizan. The white one is Wiglove. Funny names. It's the exterior tape. This one, isn't officially works to about 15, but you could probably get it to work a little bit. What you will notice with both of those tapes is they're vapor open and they're stretchy. So what that allows you to do is, if you worked with tuck tape, the red tuck tape, it's vapor closed. So if you get an air bubble, you can't get that air bubble out. With the vapor open tapes, you just push on it and the air will come out. And also because they're stretchy, they're a lot easier to fix and actually get smooth if you're not perfect. Whereas the tuck tape, if it kind of touches itself, you're kind of messed up. So these are different ways to do vapor barriers. Below grade, you can use still poly. You can use poly above grade. It's trickier to get durable, but you can use poly with high quality tapes. You can also use membranes, and you just basically are taping all of your corners like you did before. You're just being more meticulous with it. But you actually don't have to use a membrane, or you don't have to use a membrane. The vapor barrier has to be on the inside. The airtightness layer can be anywhere in the wall, or you could have more than one airtightness layer. What is often done is you combine your airtightness layer with your vapor barrier. And you can do that with OSB. If you use OSB and tape it with correct high quality tapes, and it's 7/16 OSB, that meets the requirements of a type 2 vapor barrier. And then your vapor barrier can also act as a shear for your house. So if you see on both of these pictures, if you use a membrane, you need to protect it. So this is my house, there is an installation cavity on the inside. So that membrane, and you can see the electrical is running that installation cavity. So you do your air, your vapor barrier, you do your blower door test, you make sure it's at below 6, and then you put in the installation cavity, and then all of your electrical runs, all your plumbing runs run in that installation cavity, so you're never touching your vapor barrier again. And then if you ever do a renovation, you can do whatever renovation you want. You pull off your drywall, you change your walls behind it, but you're not touching the vapor barrier. If it's that OSB, in that picture they did do an installation cavity, so you can do an installation cavity, again with OSB, but if it's OSB, that's a pretty durable material. Like if you put a screw in the OSB, if you want to put a nail up, just leave the screw there. Like that's what you do through the drywall into it. Or if you take the screw out, you could put a dab of caulking or mud it and paint it, and that will make it airtight. If you're doing a renovation, you cut away the drywall, because the drywall would be on top of the OSB. You cut away the drywall, you cut out the OSB, do your renovation in the wall behind it, then cut your drywall another 6 inches wider than the OSB, put a new piece of OSB on, tape the old OSB to the new OSB, and you're back together. And then put your drywall on. So a lot of people do put an installation cavity on. On the most recent house I designed, I didn't. I used that OSB tape for that reason. And then it just allows you to use more of the low-cost blown cellulose, dense packed blown cellulose, and not have to do as many different layers on the wall. But again, there's different options. And again, both Siga and Rotoblast and all the other manufacturers want you to succeed. They don't want you to fail your blower door test. So they have very good manuals. They have training to make sure you do it right. So it's use the right materials, keep your details simple. It's not as difficult. It's a thermal imaging view of an attic hatch. What are you seeing? You're seeing the airflow. So people always say, well, how do I know where my air is leaking?
So we're looking at the attic hatch for this home, and here we see again those wisping patterns that are telltale of air leakage. So some simple weather stripping around the attic hatch would probably have a significant impact to the air leakage of this home.
So when you do your blower door test, do you do thermal imaging camera at the same time, and you literally see where your holes are. So then you kind of, at least the first time, you plan to fail your first blower door test. You do the thermal imaging camera, then you come along with this tape and go wherever there's a staple hole or wherever there's a small hole, and then on your second test, you should pass. But you can visually see the air leakage with the thermal imaging camera. So that's why it sounds difficult, but if you use the right materials and equipment, it isn't. So that is number 2, that is airtightness. So the next of the principles is thermal bridge free. So what a thermal bridge is it's any area on the building that has a lower effective R value than the rest. So back to the coat example, if you put your coat on, zip the coat up, your zipper is a thermal bridge because there's no insulation at that zipper. So what lots of coats have is they have an insulated flap that goes over the thermal bridge to reduce it. So what we are seeing is every single stud, and wood is about R1. So you have insulation in that wall, it's probably R20 insulation. But then when you have R6 or R4.5 from your stud and nothing else, thermal bridging is coming through and melting the frost that is on the outside of that building. And this is a recent home, 2019 home in Calgary. Studs are always a thermal bridge. It's a thermal bridge you really can't eliminate. So some thermal bridges you want to eliminate, some you want to mitigate. So you want to mitigate the thermal bridges from your studs. You also want to mitigate the thermal bridges from your rim joist. So rim joists are almost always a thermal bridge. Another type of thermal bridge is called a geometric thermal bridge. That's a corner. So a corner is always a thermal bridge compared to a flat surface, because on an infinite flat surface, if you have 1 square inch of inside wall, you have 1 square inch of outside wall drawing the heat out. If you then take that 1 square inch and put half a square inch on one side of the corner, half a square inch on the other side of the corner, you still have 1 square inch of inside wall. But even at a 5.5 inch deep wall, you now have kind of half inch or 1 inch by 5, 1 inch by 5. So you have kind of 6 inches of exterior wall drawing the heat out. And then if you then have a thicker wall, like a passive house wall, you have 18 inches of depth. You got kind of like a foot of exterior wall. So you want to reduce the number of corners. So 4 would be the preferable number. Mm-hmm. Start with a rectangular square box and have a good reason to change from it. But then when you are going into a deeper passive house wall, because you have more insulation space, you can come up with details that actually totally remove that thermal bridge by just kind of minimizing how much structure relative to how much insulation you have. So that's kind of the one of the examples of the thermal bridge. Here's another example of a thermal bridge right now, because right now code doesn't require us to put any insulation below the slab. I don't know, when I go outside, I put boots on. My feet would get cold. About two meters down below grade, the temperature is the average annual temperature of the world in that location. So in Alberta, it's about 5 or 6 degrees. So 2 meters down, the ground is 5 or 6 degrees. So if you want your basement slab to be more than 5 or 6 degrees, you need to insulate it. So this is my house. So it has 8 inches of EPS foam underneath that entire slab. And the vapor barrier needs to be continuous. So what I have done is I have 2 4-inch layers. So I have put my poly vapor barrier in between those 2 4-inch layers of foam, bring it up the sides, and then can attach to the rest of the sides. So it is continuous, and because it's between the foam, it's not ripped to shreds by all that rebar and all that people walking on it. But yes, so you do need insulation below the foam, below the slab, all the way up, all the way around, if you want your basement to be comfortable. These are 2 other types of thermal bridges. So architecturally, a lot of architects kind of like the look of a beam going from the inside all the way to the outside. So if it's a wood beam going from the inside to the outside, it's kind of like a highway for heat to go out to your building. If you have a steel beam going from the inside to the outside, it's like a super highway for heat to go outside the building. So to eliminate that thermal bridge, you just cut it off. You just attach it to the structure on the outside. So then it's no longer a thermal bridge. The other example is roxel or mineral wool in between the studs. But there are a fair amount of studs. There's like studs, I think, at 2 feet going both ways. So that would be a large thermal bridge. So what they've done is they've added, I believe this is a wood fiber board. So it's about an R5 wood fiber board on top of everything to reduce that thermal bridging. So this is it. This is another type of materialist wood fiber board that you could use on the outside that you don't have to worry about condensation. It's very vapor open. If it becomes a condensing surface, the moisture will come out right away. And some of the wood fiber boards can use can take some structure, some shear. So again, this is a thermal imaging camera of a building. This is the before the passive house renovation. There's after the passive house renovation. So again, you can look at the windows. That green of a passive house window, like that glass is about, center of glass is R9 to R11, which is about the equivalent effective R value of a 2x4 wall. So the windows in a passive house are as good as a 2x4 wall. And the rest of it is all blue, no thermal bridges, all perfectly cold. That's how you get comfort and no drafts.